Hey, what's up, guys? Chung here again. So today let's take a look at another LeetCode problem, number 444, sequence reconstruction. It's a medium problem. Um, as you guys can see, it got a lot of downvotes. Even I gave gave this problem a downvote, but still I wanna talk about this problem because this is like it's just something that I wanna talk about. Okay. Okay, so it gives you a original sequence from the range is from 1 to n, right? From the 1 to the length of n, and it could be anything. It's a permutation of the 1 to n number, okay? And then the second parameter is the sequence. The sequence tells you the from like you need to have 1 first, and then 2, right? And then here is like 1 and 3. You need to have, so 1 comes before 2 and 1 comes before 3. And it asks you to return a boolean to check uh, based on the given sequences, can you uniquely reconstruct this origin sequence number here? All right, for example here, right? The sequence is 1 has to come before 2 and 1 has to come before 3. Can you reconstruct 1, 2, 3, right? No, right? Because all we know is that 1 has to be before 2 and 3, but between 2 and 3, we don't know which one, I mean, will come up first, right? So that's example 1 here. And example 2 here is that, this is it's obviously it's like it's not going to work, right? Because the sequence doesn't even include all the numbers here, right? Basically, if the sequence doesn't include all the numbers in the original numbers, basically there's no way we can reconstruct, right? And the third one is this. Yeah, so basically the number 3 is the correct version of the example 3 is the correct version of the example 1 here. So besides is 1, 2, 1, 3, it also gives you like another sequence between 2 and 3. So in this case, we can reconstruct 1, 2, 3 from the sequences here, right? So this is obviously like a graph problem, right? Because for example, there's a 1 here, and so from the first element to the second element, we're gonna have a, a directed graph here, right? 1 to 2 and 1 to 3, right? And 2 and 3 right here. So and for example, this one, there's 1, 2, 1, 3, and 2 and 3. Okay, right? So that's the graph. So and ask us to check if we can uniquely reconstruct this, right? So what we can do is we can use like topological topological sort, right? For the topological sort, one way of doing it, we use like an integrate dictionary, and where in the integrate dictionaries we always stores the current zero integrate node, right? And how can we use that to solve this problem, right? So as you can see here, so if you think about it, so let's say if there are two elements, in a 0 degree queue here, right? For example, in this case, let's say there's no this edge here. So once we remove the once we remove node, right? So both 2 and 3 will become 0 integrate, right? So that's how we can utilize this queue to help us determine if there's a unique topological sort, right? So anytime if if the length of queue is greater than 1, right? Then we know, okay, so currently there are like more than one node in the queue which have the 0 integrate, which means we can process either of them, right? Then it tells us there's no unique reconstruct or unique topological sort for this problem, right? Basically, that's the main idea. And it's just other than that, it's just a few bad case. I don't know if it's a bad cases or the description was kind of ambiguous here. That's why it got a lot of votes here because here it kind of makes sense, right? Because it's we only giving like one and two here, but there are like some really weird test cases here. For example, if the first original order is one, right? And then the sequence it gives you like sequence is like is two. It's not even like it's not even part of the notes here, right? I think it is because this problem it doesn't say it's a graph problem, right? So there's no guarantee that the sequence you cannot assume that this sequence given here is is also all of the sequence given here are part of the original sequence number, right? It could be anything, right? In this case, you know, because the reason we get confused here is because we are trying to convert this problem into a graph problem, and in the graph problem, we're always thinking, okay, all the numbers has to be in this graph, but in this case, that's not it's not always the case, right? For example, this one. I mean, the graph only has one node, but we're giving like an edge here, right? With two here, graph two here, and that's one case. And another one is this. Let's say there's a one here, right? And on the sequence here, we are given like 1 to minus 9, okay, and then 1 to minus 8, right? It's also possible, right? It doesn't because it doesn't the it's not only limited to the nodes to the numbers within the original sequence, right? It can be anything basically. So that's why in order to handle this kind of case, right? So basically we have to be limiting all the numbers like we have seen so far in the sequences is part of the original sequence, right? Otherwise, we can simply return a false because we know there's something invalid here, right? So to do that, I'm just simply using a minimum and maximum numbers to compare with the minimum and the maximum in the original sequence and the current sequence list here. If either of them is not the same, then because another thing is that in order to uniquely reconstruct the sequence here, basically all the numbers, for example here, all the numbers in the original numbers has to be appear in the sequence numbers list, right? Because otherwise we don't know the sequence, right? So that's why I'm using the minimum and the max numbers to constrain the the output. And okay, so with that being said, let's try to code here and orgs, right? So like I said, I'm gonna finish the graph here. So the graph gonna be the dictionary and it's gonna be the list, and then I'm gonna have an integrate dictionary as well. So this is like default dictionary int here, right? And then I'm just going to uh, look through the sequences here, right? So the sequence uh, in sequences, all right? And then basically, for example, with this like this list here, right? So basically everything from the first one to the next one, for each of the combinations, I'm going to create a edge in the graph. For example, this one, 5 to 2 is an edge, 2 to 6 is an edge, 6 to 3 is also an edge, right? Okay, so and that's why I'm not gonna graph. Okay, so for right for I in range to the length of sequence, right? -1 because we'll always be moving to the next one to make sure it won't out be out of the boundaries. So that's why I'm doing a length -1 here. And then the graph dot So the start is the current number, right? That's the I, right? And then the the end the end is the next number basically. Sequence I minus plus one, right? Same thing for the integrate, right? The integrate is simply just uh the next one, right? So it's the two node plus one, I plus one and plus one, right? That's the how we construct the integrate. And like I said, um, I'm gonna have like a minimum and a maximum value here, right? Minimum uh, number, maximum number equals, oh, sorry. The minimum number, we have to be initialized to the max size, and the maximum number has to be okay, right? So basically, every time here, right, we just simply maintaining this minimum and next number that we have seen so far in this all the sequences here, right? So minimum gonna be the minimum of that of what? Of the minimum number we have seen in this sequence, right? So we're gonna have a minimum of the sequence. Same thing for the maximum number, right? Maximum max, right? So that's how we maintain the minimum and max number. So and here, before doing anything, we can simply do a check, right? If uh, if minimum number is not one, right, or the max number is not equal to n, right, then we simply return false because we know then the sequence is not valid, right? So okay, so once we we finish that checking, now it's safe. We can finally get on to the real topological sorting algorithm here, right? Basically, we create a queue here, right? So this is like the queue to hold the all the nodes that have the zero integrates, right? To start with, we have to uh, uh, okay, collections DQ, right? And then I'm gonna start it with the what is that? Sequence, not sequence, the number, okay? For number in range, right? In range 1 plus n plus 1 because the range is from 1 to n, right? That's why to start with, I just need to get the current zero integrate node, which is the ones that does not exist in this integrate node, right? Because anything that exists in the current integrate node has an integrate value, right? And to think it in a opposite way that anything that's not in this integrate has a zero integrate. Okay, if sorry here if num not in integrate. All right, and now for the while queue here, right? So like I said, anytime we do a check if the length of queue is greater than one, then we simply return a false here. Okay, and then node equals to queue dot pop left, right? And then for the neighbors, right? For neighbor in graph, yeah, in graph node, yeah, in graph node here, and we'll be removing the integrates from that, right? Integrate neighbor minor, we decrease it by one, and then we check if this integrate is become to zero, right? Of this current node neighbor node is equal to zero, then we can simply add this add the final one. Uh, yeah, we can simply append this neighbor to the queue here. Okay, and then in the end, yeah, in the end, okay, sorry. So how can we track, right? How can we know if it can be reconstruct to the correct answer, right? So we need to have like an answer, right, to hold out the current topological sort result we have here, right? Basically, every time when we have a zero integers, we we append it to the answer here, and in the end, we need to compare, right? If the answer we got from this like reconstructing the sequence here is the same as the origin, all right? Right? If they're the same, then we know okay, it's it's true, right? Like for example, this one, the answer we got from this topological sort is 1 and 2, and but the original is 1, 2, 3. That's why it's false, right? Okay, I think that should just work. Okay, let's try to submit it. Cool. So it passed. All right, so it's kind of like an interesting like topological sort or graph problem, right? And basically we're using this like a queue. We check the length of the queue to figure out if there's a unique way of reconstructing to basically to get the unique topological sort answer, right? And the little a few edge cases is to for the invalid sequence number here, right? Which does not exist, which don't exist in this original list. That's why I'm using a minimum and a maximum value to do a pre-check here, like this one, right? And then after that, it's just the regular topological sorting by using the integrate uh, dictionary, right? And in the end, we simply return the answer with original answer. Okay, cool. I think that's it for this problem. Yeah, thank you so much for watching the videos and stay tuned. I'll be seeing you guys soon. Bye bye.